Okay, so now we move to the next part of our lesson, horizontal oscillation. Okay, so we can investigate the motion of a particle which is attached to an elastic spring or string and is oscillating in a horizontal line. Okay, so we are going to investigate particles attached to elastic spring and string. Okay, so in this case, when it comes to horizontal oscillation, it actually matters whether you are attaching to a string or a spring. It actually matters. Okay, so we will see how to deal with each of them separately. So first, I will be taking you through how to work with elastic springs. Okay, so first I'll take you how to work through elastic springs. Okay, so in exercise 3D, question number 1, let's read this. A particle P of mass 0.5 kilogram is attached to one end of a light elastic spring of natural length 0.6 meters and modulus of elasticity 60 newtons. Can you see? So natural length is 0.6 meters, lambda is 60 newtons. The other end of the spring is fixed to a point A on the smooth horizontal surface on which P rests. The particle is held at rest with AP equal to 0.9 meters and then released. Show that P moves with simple harmonic motion. Okay. First thing is, let's quickly draw a sketch of the diagram. How does it look now? So you have a horizontal spring. So you have a spring like this, right? Okay. Okay, so this is your particle. The natural length of the particle is 0.6. The natural length of the spring. The natural length of the spring is 0.6 meters. And they say here, this other end, they are naming this it as A, right? A particle P, mass 0.5 kilograms. Mass is 0.5 kilogram attached to a end of a light elastic spring. Natural length 0.6 meter. Modulus of elasticity 6 Newton. The other end of the spring is fixed to a point A on the smooth horizontal surface. Can you see the point A on which P rests? The particle is held at rest with AP. With AP 0.9. So if AP is 0.9, what have we done here? If AP is 0.9, what have we done here? Now you know normally the spring would want to be in its natural length, isn't it? But then you can see AP is 0.9 means what? So this is A. AP is 0.9 means you have stretched how much? AP is 0.9 means you have stretched 0.3 meters. So you have moved this particle 0.3 meters away from its equilibrium position. Are you with me? Okay, because the particle would naturally want to stay here. Can you see? This place that I'm mentioning right now, the natural length. This is the place where the particle would naturally want to be in. But we have pulled it a distance of 0.9. We have extended it a distance of 0.3 meters. So away from the equilibrium position. So first thing I want you to notice here is, I want you to understand is the equilibrium position, the place where the object wants to stay. That particular point is going to be the center. That point is going to be the center of your simple harmonic motion. So what's happening here? Now the particle would naturally want to be in its natural length like this. So this place where the particle would be in equilibrium, naturally in equilibrium, will be the center of your SHM. And how much are you disturbing? How much are you pulling it initially away from this center? From the center, from the equilibrium position, how much are you displacing it? You're displacing it 0.3 meters, right? So that is the initial displacement. So this initial, the amount that you are moving from the equilibrium position, the initial amount you move from the equilibrium position will become the amplitude of your simple harmonic motion. Yes, we are going to now have simple harmonic motion here, right? You are going to release it from this point. So when you release it, the particle will perform simple harmonic motion. The particle will, so the amplitude here, this amplitude is 0.3 meters. The amplitude, the amount, the initial amount that you move the particle from its equilibrium position, the initial amount, whatever the amount you move initially from its equilibrium position becomes the amplitude. And then, okay, so then the particle will now do what? It will perform simple SHM, it will perform SHM about the center with amplitude 0.3 meters. Are you with me? So all the previous rules that you that you learned will apply now. Okay, so all the previous rules, in the sense you remember all the equations we learned, the x equal a sine omega t, x equal a cos omega t, v square equal omega square a square minus x square. So all those equations can be applied for the simple harmonic motion. Are you with me? So in the previous exercise, we learned how to use those formula, right? Okay, so now they are saying in part A, now you're releasing it, right? So you're releasing it from this point. So you need to realize the moment you release it, the particle will start to move towards the center. Isn't it? It will start to move towards the center, increasing in speed. And at the center, it will reach the maximum velocity. Isn't it? And then it will start to, the spring will start to compress and it will go to the other side, an amplitude of 0.3. And again, it will start to come back. So you will perform, this particle will perform SHM. Okay, right. So then the question is to show that P moves with SHM. How do you show that a particle moves in SHM? What is the characteristic, the main characteristic that defines simple harmonic motion? So there is one very important characteristic, that is the acceleration is proportional to the displacement. Acceleration is always directed towards the center, which means any object or particle that performs simple harmonic motion will always have its acceleration function with this characteristic equation. X double dot will always be following the format minus omega square x type of format. Minus because acceleration is directed towards the center, and omega square will be a constant, and x is the displacement. So any particle that moves with SHM should have acceleration function that follows this particular order. So all you have to do here is, if you want to show that your particle moves with simple harmonic motion, all you have to do is show that the acceleration function is looking something like this. It looks something like this. That's all you have to do. So to do this, what we need to do here is we will consider this particle at a general position. What do you mean by a general position? Now, you know, at this point over here, this is a very specific place, right? Okay, so I will consider this particle at another, through its motion. Okay, so you can see again, I'm drawing the same thing. Okay, so the same diagram, I'm just drawing it down here, as you can see. This is the point A, the amplitude. So you can see now in my diagram, the particle is not at the amplitude. Can you see? This is the amplitude, but it's not at the amplitude. Can you see? It's somewhere somewhere in the middle of the motion. Can you see? So normally, how do we measure the distance? The distance is always measured from the center of the SHM, and you measure the distance in this direction, right? Away from the center. X is measured from the center of the simple harmonic motion, away from the center. Do you agree with me? Okay, so this is how you have. So what we do here is we are going to apply F equals MA at this general point. So this is a general point. Why do I say it's a general point? Because there is an unknown displacement at this point. There's an unknown displacement. So the particle is midway moving over here. So I'm going to apply F equal MA at this general point. That's all you have to do. Apply F equal MA and show that the acceleration function looks like this. Okay, so what are the forces acting while the particle is over in this general position? What are the forces acting? This is a general position because we do not know the displacement. The displacement is given in terms of x. Okay, so what are the forces acting at this point? You have the weight, okay? You have the weight, you have the normal reaction. But the thing is, this is moving horizontally, right? So will the weight, normal reaction, which are vertical forces, make any impact on this horizontal motion? No. Okay, but this is a smooth flow. So therefore, you won't have friction. You will have tension. It's the tension that's pulling this right towards the center. So you have tension. So the first force you mark here is the tension. That's the only force you have because we do not have any opposing reaction. We do not have any other horizontal force. There is no friction. Okay, so tension is directed towards, this is the way it's pulling, right? Tension is pulling the particle towards the equilibrium position. Okay, in this case, when it's moving back over here. Are you with me? Okay, so now time to apply F equal ma. F equal ma, we apply always these equations away from the center. Okay, we will be applying the equations away from the center because away from the center is what we consider as the positive direction. And then you need to show that the acceleration will become negative because you are applying the equation away from the center. Okay, so what are the forces? I'm applying it away from the center. Can you see? Normally, that's how we usually apply. Okay, because away from the center is what we consider as positive. Okay, so what's happening here? The tension is towards the center. Can you see? Which means it will become, I will write this as what? The force is a minus T. Do you agree with me? It's minus T. Minus T equals, that's all right. That's the only force we have. What's the mass? Mass is 0.5 kilogram and acceleration is what we are trying to find. So acceleration function we denote as x double dot. Isn't it? Do you recall? We call the acceleration function acceleration as a, in this particular lesson, when acceleration is a function of displacement, we write it as x double dot. That is acceleration. So how do we find the value of the tension? By using Hooke's law. So lambda x over L. So input the value minus lambda x over L. The minus mark is there because the tension is towards the center. But we consider the equation F equal ma always away from the center. That's why you have the minus mark here. Okay. So from the beginning we learned away from the center is what we consider. Right? Whenever we are doing these things, we take away from the center. In chapter 1, do you recall? Even in chapter 1, away from the center was positive. Okay, so then let's get the tension. Tension is lambda x over L. Can you input the values? Lambda value is 60 newtons. And extension, the extension in this case is, remember in here the x doesn't mean the distance that you have displaced from the center. In Hooke's law, what does x represent? In Hooke's law, x represents the amount that the spring has extended beyond its natural length. So is that what's the value here? Now you can see in this case also natural length is 0.6 meter. So actually you can see in this case the simple harmonic motion displacement and the extension of the spring are actually the same, right? In this case, but there will be cases where it will be different. There will be cases where it will be different. So I will show you when we go through the sums where it differs. Okay, but in this situation, in this particular question, the the x value from the displacement for the simple harmonic motion and the extension of the spring are both the same. It's the same x. Can you see? Because x is the amount the spring has extended beyond its natural length. So here x value is directly x divided by natural length is 0.6. So can you all simplify? 60 divided by 0.6 is 60 divided by 0.6 is 100. So tension is equal to 100x. Shall we input the value? So minus 100x equals 0.5 into x double dot. So when you make x double dot the subject, half comes down, minus 100x divided by half. How much is it? Minus 100 divided by half is, so minus 200x. Can you see the characteristic equation of simple harmonic motion? X double dot equals to some minus constant times x, and I get it perfectly. Can you see? So this is the characteristic equation of SHM. So I get such a equation. So in that case, definitely what do we write? Therefore, we realize that this particle will move in simple harmonic motion. So you can write therefore. So the moment you get this equation, the moment you get this x double dot equation correctly, it means it moves in SHM. You can write therefore particle moves in simple harmonic motion. Okay, so this is the first part. And then part B, they are saying find the period and amplitude of the motion. So how do you get the period and amplitude? Part B. Okay, so then the next thing is to find the periodic time. What we do is you can see that periodic time is equal to what? 2 pi over omega in simple harmonic motion. 2 pi is a constant, omega is a constant which we need to find. So you can see by looking at the characteristic equation of SHM, it follows the format x double dot equal minus omega square x, right? Which means what? You know the value of omega square. So over here, omega square value is omega square value is 200 because x double dot equal minus omega square x. Minus mark is there. Omega square will just be the 200. Isn't it? X double dot equal minus omega square x. So 200 is in place of omega square. So omega square is 200, which means omega is root 200. Can I know the value? 10 root 2. So T equal 2 pi over omega is 10 root 2. So you could simplify pi over 5 root 2. And maybe rationalize also. Anyway, we'll keep the answer in exact form. So if you rationalize, you get periodic time equal root 2 pi over 10. Can you understand? Part C. Sorry, not part C. We also have to get the amplitude. So what's the amplitude? Do we need to perform any calculations to find the amplitude? No, we do not need to do any calculation to find the amplitude. Why? Because I told you at the very beginning, the initial amount that you are displacing from the equilibrium position, the amount that you move at the very beginning, that amount that you move when you release, that place where you release at the very beginning becomes the amplitude. So at the beginning, the particle is naturally at 0.6, but you have taken it to 0.3 meters and you are releasing from that point, which means the amplitude will immediately become what? 0.3 meters. You do not need calculations for this. Okay, so that's the maximum displacement from the center. Part C, to calculate the maximum speed of P. How do you calculate the maximum speed? We know the rule that where do we achieve the maximum speed? At the center. So Vmax occurs at the center. So Vmax occurs at the center means X value is 0. Isn't it? Part C, Vmax occurs when X is 0. Are you with me? So V square equal omega square A square minus X square. So V square is what we are trying to find, right? Omega square is 200, amplitude is 0.3 square minus X is 0. How much is the value? (200 into 0.3 square). How much? 18. So V is root 18, right? Which gives me 3 root 2. 3 root 2 meters per second. This is the maximum speed. Okay, so next I'll move to question number 5. So first I'll be focused on questions that are related to elastic springs. So first I will be doing questions related to elastic springs, and then I will go to questions related to elastic springs. Okay, right. So question number 5. A particle P of mass 0.6 kilogram is attached to one end of a light elastic spring of modulus of elasticity 72. So lambda is 72 newtons. Natural length is 1.2 meters. The other end of the spring is fixed to a point A on a smooth horizontal table on which P rests. Are you with me? So, okay, so this is the place where we start. The end A, the other end of the spring is fixed to a point A. Okay. And over here we have the natural length. Natural length is 1.2 meters. Okay, and then initially P is at rest with AP 1.2 meters. So initially what's happening? The particle is at rest with AP 1.2 meter means you need to realize it's at its natural length. Are you with me? The particle is at its natural length. Initially, the particle is at its natural length, AP 1.2 meters. The particle receives an impulse of magnitude 3 Newton seconds in the direction AP. So this is AP, this is P. So it receives an impulse. It receives an impulse in the direction AP. So in the direction AP means it receives an impulse in this direction. Are you with me? The impulse it receives is 3 Newton seconds. Can you see? And then because of the impulse, what's going to happen? Because of the impulse, what's going to happen? The particle will receive a velocity. The particle will receive a velocity and will start moving away from the center. Will start moving away from the natural length because of the impulse. So they are saying, given that t seconds after the impulse, the displacement of p from its initial position is x meters, find an equation for x in terms of t. Now in this particular question, can we just look at the sum and deduce the amplitude? No, in the previous question we did, they told us exactly the amount that they initially pulled. But in this one, we can't do that. Are you with me? So in this one, we cannot just use the initial amplitude now because we do not know how over here they are saying they are giving an impulse. So it's the impulse that will cause the particle to move. Okay, the first thing you should do here is you have to show that the particle, you have to show that find an equation for x in terms of t means what? An equation for x in terms of t means you have to get the relationship between x and t. So basically, what equation can we use to get the relationship between x and t? What equation can I use to get the relationship between x and t? Yeah, we can use. Normally, if you are starting your movement from the center, you can see this is the center of your SHM, right? So if this is the center of your SHM, and if your particle starts moving from the center, we can use x equals which equation? X equals a sine omega t, isn't it? Because you remember there are two equations, x equal a sine omega t, x equal a cos omega t. X equal a cos omega t is used if the particle starts its motion from the amplitude, from the corner point. But you can use x equal a sine omega t if the particle starts its SHM motion at the center. So over here you give the impulse at the center, which means the particle begins its simple harmonic motion at the center. So anyway, before you do that, I think you need to realize we need to find the omega value. We need to find the amplitude. So to do that, you will first have to what? You will first have to prove the characteristic SHM equation. You'll first have to prove the characteristic SHM equation. So that's the first thing to do. That's the first thing to do. Okay, so we'll use this. Okay, so this is, I'm considering the particle at a general point, okay? This is the center, so we measure x away from the center. So this is a general point. Okay, so amplitude might be a little bit away. Can you see? The amplitude might be more over here. Can you see? So this is the particle somewhere moving midway. So all you have to do is now what? Apply F equal ma first. Apply F equal ma and find what? And get the characteristic simple harmonic motion equation. That's the first thing to do. Okay, so let's apply. Okay, the x value is the displacement that the amount the particle has displaced away from the center. Okay, x is not the amplitude. X becomes the amplitude only at the very corner. That's a very specific point. But when you are over here, x is a variable. Okay, so x could take any value between b0 and a over here. Okay, so x is a variable. So this is a general point. So what are the forces acting at this general point? You have the tension, right? You have the tension. You have the tension. So let's apply F equal ma, and we always apply F equal ma away from the center of the SHM. So what are the forces we have? The tension is acting towards the center. Therefore, it's minus T equals mass is 0.6 into acceleration is x double dot. Let's get the tension. Tension is lambda x over L. Input the value. Lambda is 72 into extension is the distance that the spring has stretched beyond its natural length. So beyond the natural length, this is the natural length, right? You know that this is the natural length. So that the amount the string has stretched beyond its natural length is this x, right? So that's x divided by natural length is 1.2. Can I know the simplified answer? 72 over 1.2 is 60x. So tension is equal to 60x. So let's input the value here. Minus tension is 60x equals 0.6 x double dot. So x double dot equals minus 60 divided by 0.6x. How much is the answer? Minus 100x equals to x double dot. So can you see that I have got the characteristic equation of simple harmonic motion? X double dot equals minus 100x. Okay, so to get the equation for x in terms of t, we are not done yet. So the characteristic equation is x equals a sine omega t, right? So I think omega value is done. We have the omega here, but we need the amplitude, isn't it? Because we use x equal a sine omega t, we need the amplitude. How do we get the amplitude? Now remember, amplitude is a constant. Okay, remember here, this x value, the displacement from the center, this x, the maximum x value you can possibly have is x equal a. And a is the amplitude value is a constant. Okay, x equals a is a very specific point and that only occurs at this corner. Do you understand? So x equal a only occurs at this corner, not anywhere in between. X is a variable. So while the particle is moving in between, the x value is changing. When the particle comes to the last possible moment, the corner, then x is equal to a. Okay. So how do we find this amplitude? This constant length, the maximum length you are possibly moving. So the way we do this is, you can see we have the impulse given, right? So we can use the equation impulse equals to what? I equals to mv minus mu. Do you recall? Impulse is equal to change in momentum. I equal mv minus mu. So impulse is 3 Newton seconds, right? So mass, what's the mass? Mass is 0.6 into what's the final velocity? V means the speed you achieve after the impulse. And u means the speed you have before the impulse. Now, you know, at the beginning, the particle was at rest here, isn't it? So actually, when you use I equal mv minus mu, v is the speed that this particle has immediately after the impulse. And that is actually what I want to find, right? So 0.6 into v minus mass 0.6 into what's u? U is 0 because at the beginning it's 0. So 3 equals 0.6v minus 0.6 into 0 is 0. How much is the velocity at the center? 3 over 0.6v is 5 meters per second. So guys, if this is the speed that you achieve at the center, that speed is also known as what? Because that's the speed you are leaving at the center of your SHM. So that speed is the Vmax. The maximum speed is 5 meters per second because that's the speed that you have at the center of the SHM. So that is the V max. So V max is 5 meters per second. Now what do? We use the equation V square equal omega square A square minus X square. At V max, X is 0, right? At V max, X is 0. So V max is 5 square equal omega square is 100. Amplitude is what I'm trying to find. A square minus X is 0 because at V max, X is 0. Are you with me? So let's get the amplitude value. So this is 25, 5 square 25 over 100 equals to A square. That's 1 over 4. So root of this, right? Root of 25 over 100 is equal to A, which is A equals half, 0.5 meters. Can you see? So this is the amplitude. Okay, so moving on to part B, calculate the maximum magnitude of the acceleration of P. Guys, where do we find the maximum acceleration? So you need to recall the theories of SHM. In SHM, so I have given you this theory before in the previous section. The maximum magnitude of acceleration is found where? At the center or at the amplitude? At the center, the velocity is maximum. Maximum velocity means at the center acceleration is 0. Do you recall? At the center acceleration is 0. Let me show you. So this is the initial diagram that I showed you at the very beginning, right? In SHM, at the center you have maximum velocity. At the end, the acceleration is 0. At the center, x double dot is 0. But at the corner, at the amplitude, you have the 0 velocity, but your acceleration is a maximum. Are you with me? Okay, so then let's get the answer. Okay, so that's part B to calculate the maximum magnitude of acceleration. I think I had to first, I did not get the equation for part A, right? Because the part A equation is find an equation for x in terms of t. I didn't get it. So x in terms of the equation is x equals a sine omega t, right? So x equals a is 0.5. Remember, amplitude is a constant. X is the variable. Amplitude is the constant. Sine omega square is 100, isn't it? Omega square is 100, omega is 10. So x equals half sine 10t. X equals half sine 10t. So that's done. Part B, the maximum magnitude of acceleration. Where do we find the maximum acceleration? Maximum x double dot is found where? At the amplitude. You have the maximum acceleration at the amplitude. So x double dot equals minus omega square x. X double dot equals minus omega square 100. X is the maximum x value is a, right? The maximum x value is a. It's at the amplitude. So that at the amplitude x is equal to a. So amplitude is equal to half. Are you guys with me? So how much is the maximum magnitude? The magnitude means we do not need I do not need the negative positive signs. All I need is the magnitude. So what's the magnitude of the acceleration? The magnitude of the acceleration is, so its minus will be gone. 100 into 0.5 is 50, right? 50 meter per second square. So this is the maximum magnitude of our acceleration. Okay, so next I will do another question involving springs. So this is question number 7. A smooth cylinder is fixed with its axis horizontally. A piston of mass 2.5 kilogram is inside the cylinder attached to one end of the cylinder by a spring of modulus of elasticity 400 newtons. Okay, so you have a piston. The mass is 2.5 kilograms inside the cylinder attached to one end of the cylinder by a spring. Modulus of elasticity 400 newtons. Natural length 50 centimeter means 0.5 meters. The piston is held at rest in the cylinder with the spring compressed to a length of 42. Guys, so what's happening if the spring is compressed? So you have the spring over here, the starting point. Okay, and then the spring is, they are saying, so this is the weight, the piston. Okay, so they are saying here that the natural length is 0.5 meters. The natural length is 0.5 meters. And what are they doing? And what are they doing? They are saying the spring is held in rest in the cylinder with the spring compressed to a length of 42. So they are compressing it to a length of 42 means what are we doing here? You are compressing it to a length of 42 means how much are you displacing from the center? Guys, I told you whatever the distance that you are displacing away from the center, immediately the initial amount you displace away from the center will immediately become your amplitude. So how much are we displacing? 0.50 centimeter to 42. How much is the difference? 50 centimeter is now becoming 42 centimeters, which means we have compressed how much? We have compressed 50 centimeter to 42 centimeters. We have compressed 8 centimeters, 0.08 meters, and that will become the amplitude because that's the amount that you initially took from the equilibrium position because this is the center of your SHM. The equilibrium position is the center of your SHM. That the amount that you displace from that center is always the amplitude. So the amplitude amount here is 0.8. The amplitude is 0.8 meters. 0.08, right? 0.08 meters. So this is the amplitude. Okay, and then they say the spring can be modeled as a light elastic spring and the piston can be modeled as a particle. So find the period of the resulting oscillation. How do you find the period of the resulting oscillation? First thing to do is to apply F equals ma. So you can apply F equal ma at a general point. So the general point, actually, the general point can be anywhere. Guys, you need to realize that this spring, when you release from here, it will move to the other side also, right? Like this, it moves onto the, because it will move to the center and go to the other side. Again, it will come back. So it's going to move like this, right? So I will consider the general point in a easy position for me. So I will consider the general position over here. Can you see what I just did? You could consider this general position even over here. That's fine. So if you consider the general position over here, then in that case, now you need to understand in this spring. Okay, in a spring, I think you need to understand one small thing here. Okay, let's say our particle, you're going to consider the general point over here. Okay, so in this case, the spring is still compressed, right? Which means what? Are you having a tension now? It's a thrust. So that's really important that if you mark the force, you have to mark it in this manner, thrust. Okay, and X is measured away from the center. So I prefer to have my object on this side. So always, so that I can have, I will mark it on the other side. So if when I pass the center, what is there in the spring? So once I pass the center of the SHM, the spring will now have what? Not thrust, but it will now have tension. Okay, because now the particle is always trying to move towards the center, right? So it will now be pulling. But when you were over here, it was a push, it was a thrust. But when you're on the other side, it becomes a pull. So those are things you need to understand. Okay, so then this is the center of the SHM. And so this is X. This is X. Okay, so we'll apply what? F equal ma at the general point. So amplitude is somewhere over here. So let's say amplitude is 0.08. And then we'll mark the tension. So we have the tension here. Let's apply F equal ma away from the center. So what are the forces we have? The tension is towards the center, minus T equals mass is mass is 2.5, right? 2.5 into x double dot. So tension is lambda x over L. Lambda value is 400. X is the distance that the particle, that the string or spring has stretched beyond its natural length. So this is the natural length, right? Natural length is 0.5 meter. That's this. So beyond the natural length, we have stretched a distance x. That's x over natural length is 0.5. How much is 400 divided by 0.5? That is 400 divided by 0.5 is 800. So 800x. So let's input the value here. Minus 800x equals 2.5 x double dot. So x double dot equals minus 800 divided by 2.5 x. How much is it? 800 divided by 2.5 minus 320x equal x double dot. Can you see we get the characteristic equation of simple harmonic? X double dot equal minus 320x. They are asking us to find the period of the resulting oscillation. So how do you find the period? Period equal 2 pi over omega. Periodic time t equal 2 pi over omega. So 2 pi over, what's the omega value? Omega square is 320. Can you see? So omega will be root 320. Shall we go for an exact answer? This is the 2 pi over, what is root 320? That's 8 root 5, right? And you could rationalize by multiplying up and down with root 5. Two root 5 into pi, 8 times 5, that's 40. Do you agree? That also we can simplify root 5 pi over 20. Do you agree? Okay, so 0.3512, it goes on like that. Okay, so it's 0.3512, correct 3s. So, you could leave your answer in exact form, or you could leave your answer in 3s. So they will let you know in the exam in which manner you should keep. Okay, so this is the period of the resulting oscillation. Then part B, they are asking you to find the maximum value of the kinetic energy of the piston. So what's the maximum value of the kinetic energy? Now you know kinetic energy is half m v square. Basically, kinetic energy depends on the velocity, the speed. So where do you, so if you want the maximum kinetic energy, you need to find the maximum speed. So where do you get the maximum speed? In this question, always in SHM, maximum speed occurs at the center of the SHM. So maximum speed. The maximum speed occurs when x is 0. Are you with me? So we can apply v square equal omega square, a square minus x square. V square equal omega square is, which is found out, omega square is 320. Right? Omega square, not omega. Omega square is 320 directly. Amplitude is 0.08, right? 0.08 square minus x is 0. Guys, can I know the answer here? 320 into 0.08 square is? How much is it? 320 into 0.08 square. That's, I get here v square is 256 over 125 in the calc. So v is the square root of this answer. and I get 16 root 5 over 25. Actually, I don't need the V value. I need the V square because the question is asking us to get the maximum kinetic energy, right? So what is the maximum kinetic energy? Kinetic energy is half m V square. So half mass is 2.5 into V square. So directly use the V square value. V square is 256 over 125. So give this value in the cal, half into 2.5 into 256 over 125. So we get 64 over 25. 64 over 25 joules or 2.56 joules exactly. That's an exact answer. Okay, is this clear? That's part B. Okay. And this is actually part A, right? Yeah, this is part A. This is part B. Okay, so this is all you need to know about working with a single spring. Okay, so in the next part, I will be teaching you how to work in the same exercise, how to work with elastic strings. Okay, so yeah, so we'll learn about that in the next part.